Hey guys, sorry I'm not here today. So here's kind of a crash course to our lesson for today. So our objective for today is to be able to create and interpret graphs and equations of objects that are being launched in the air, obviously falling to the ground. So as always, kind of like what we do in class, right? After you're done writing that down, I would highly suggest, pause the video and attempt the warm up. And what I'm going to do is I'm going to pause the video and I'm going to fill in the answers and then I'll explain how I got them. So the warm up is a cannon is 10 feet off the ground. It launches the cannonball straight up with a velocity of 406 feet per second. So I'm going to go ahead and underline what I think is some important information. And even more important, there is no gravity in this situation. So the cannonball is increasing its distance at a consistent rate. And so that's important to note. Okay, so I'm hoping you pause the video because now, bam, all the answers are there, right? So what's happening is that every second I am adding 406, right? Because it says 400 feet per second, right? So every second I'm gaining 406 feet. And so this is a linear function, which kind of helps me to derive this expression here for t time. And so to answer this second question, it says write an equation using d to represent its distance. So I'm just going to say, okay, d is equal to 10 plus 406t. Now, if you had the 406t and the 10 switched, totally fine. It is the same expression. So now we're going to move on into our first example here, kind of more realistic. So it says earlier you completed a table a moment ago that represents the height of the cannonball in feet as a function of time in seconds. Now, there was no gravity, so let's make it an actual realistic. So this is actually what happened when a cannonball was launched. Someone recorded the distance, and we're going to just take a moment, and it says to observe some commonalities or differences between these two tables. So if I were to look, let's see if I can get a little fancy here and get a little pointer. Okay. So if I looked at 416 and 400, the difference there is obviously 16. And then if I were to look at the difference or calculate it between 822 and, 758, the difference there is going to be negative 64, or subtract 64. Now, if I were to continue this pattern, I would find a difference of 144, and then I want to say it's 256 in the next one. So these numbers should look familiar to you because we talked about these yesterday. This is the effects of gravity. So effects of gravity. And we talked about the equation that represents gravity from yesterday. So hopefully you're thinking about that. And that equation is that negative 16t squared. So now I'm going to represent both of those tables in a graph. So what I'm going to do here is like I kind of did for the warm-up. I'm going to pause the video and I'm going to plot my points so that you're not like listening to me plot my points and struggle. And then I'm going to do the same for the second table. Okay, so here are the points from table 1. And obviously we're estimating. And so I'm not going to be perfect, right? So you can tell that one of those points is off. But this is going to be table 1. We know is linear. It created a straight line. It all checks out. So now I'm going to do the second table. Okay, so my blue dots are the second table. They share a y-intercept. So I just circled it so you can see that they kind of overlap there. At the 1 second mark, they're practically the same, right? There's only a difference of 16. And then that difference starts to continuously get bigger. And then I can kind of start to form, I don't know, it's a very wide U, if you will. Right, so that's all I know, but if I had to keep going, I could probably predict that it's going to keep going and then eventually hit the ground, right? That was probably a poor sketch, but you get the idea. So how are the two graphs alike? Well, they share the same, so a y-intercept, right? They both start at 10. What's different is that one's linear, first of all. That's like the dead giveaway. One's linear versus the other one's creating this upside down U, right? And what do we know creates an upside down, or I should just say a U in general, is a quadratic, right? Or in other words, I'm going to really zoom up on here just so I can kind of fit this in. But linear doesn't have gravity, right? No gravity versus the quadratic has gravity. All right, so now I actually have enough information. I could write an equation to model the situation in which I use gravity. So my distance is going to be equal to, now think about the two situations. They both start at 12, and they're both being launched. It's quite literally the same problem as our warm-up, so I still have the same velocity. But now I am taking into consideration gravity. So now I can dissect this equation and identify key parts, right? So here's my y-intercept, which is also just my initial value. And then 406t is my velocity. And of course, we know our gravity at the end. Okay, so now we're going to look at another example, and just a friendly reminder, if at some point I go too fast, like, you can rewind. So now we have a new function. We are just going to practice identifying those key points that we just addressed in that last example. So starting with 50, hopefully you're thinking, oh, that's my y-intercept, or my initial height. The 312t is my velocity. And then, of course, here is gravity. Now, because I'm not here with you guys today, we are going to skip the technology part. Maybe I'll show you guys that tomorrow. So instead, I'm going to tell you what the graph will look like. I'll actually just pull it from Desmos. Okay, so as you can tell, I went to Desmos and I took a screenshot of what this equation would look like. So what I would suggest you do is I'm gonna write this out just in case no one's listening to me and you're just watching the visual. So sketch this in your notes, because we are going to talk about some of the key features of this graph and like what information does it tell me. So starting with, here's my y-intercept, right? My y-intercept, oh, I don't like how I wrote that. Let's try that again. Y-intercept, which is my initial value, or my initial height, my starting height. Now, key features, boom, right here. My vertex, which hopefully you're thinking, oh, that's my max, my maximum, is going to tell me, so it tells me when, oops. Sorry, it tells me when and how high the cannonball gets, right? So my maximum height and when it happens. And then my x-intercept, which huge, I really want you guys to make this connection that we call this our zeros, or it's technically not a plural moment in this case, it's just one. So really, I should erase the S. It's a zero because that's when the height is 0. And let's see, if I had to estimate these values, because that is what our next question is going to take us to. So let me shift this. Oh, hold on a second. Let me play around with this, and then I'll get out of the way. Okay, sorry, I have shrunk that image. So when I am answering question B, where it says estimate the maximum height, I'm looking for that vertex, right? And so this would normally be given to us like in the graph. So you could see it's past the 1500 mark. But if I'm using my calculator, it can give me a more precise answer of about 9.5 and somewhere around like the 1,548 mark. Okay, give or take a couple, because we're estimating this, right? When does the ball hit the ground? So this is my x-intercept, or that 1, 0 that we have, which is happening, it's almost at 20. It's like 19.7. Okay, so my domain are going to be those x values, right? Like I can't have negative time. So I know it's going to be all real numbers starting from 0 to when it hits the ground, which is at that 19.7 mark.